Okay, let's take a look at 5.3, which is the idea of the multiplication rule mainly, and then this idea of independence. So two events E and F with positive probability are independent if and only if probability of E given F is equal to the probability of E. Now, you don't have to worry so much about this, but mainly I want you to note that when the events are independent, we have what's called the multiplication rule for independent events. And so the probability of E and F essentially becomes the product of the two probabilities. So let's take a very simple example here. Find the probability of getting 5 heads in a row and tossing a fair coin. So again, the sample space is heads or tails. The event E is the probability of heads. And so we want to know probability of getting heads on the first toss, on the second toss, third toss. And so this is essentially going to be, since they're all independent, and the way that we think about this based on the definition above, let me do this real quick. So we're saying the probability of, and let's make sure that yeah, there we go. Okay, probability, make sure I use probability of E given F is equal to the probability of E. So let's look at what this means. So what this means in terms of the coin, the probability you get heads on the second toss given you got heads on the first toss, is that equal to the probability of heads on the second toss? Well, knowing this is kind of like this is red given, this is the way to think about it. And then the event F, I want you to think about that as new information. Okay, so knowing that heads came up on the first toss, does that change the probability? No. So knowing this probability here is the same exact as that probability. So these two events are independent. And that means we just multiply all the probabilities together times on the third times heads on the fourth times probability heads on the fifth. And so this is essentially 1/2 times 1/2 times, or 1/2 to the fifth power. All right, so let's scroll down a bit and take a look at another example. Okay, so 13% of the population is left-handed. If two people are randomly selected, what's the probability both are left-handed? What's the probability at least one is right-handed? Okay, so one of the first things that you want to ask is you want to ask, are these two events independent? So basically, does one event affect the other? And so an easy way to think about this is if you have 100 people, probability, the first one is left-handed is 13 out of 100. Probability the second individual given the first one was left-handed is 12 out of 99. So technically these two events are not independent, but since the sample size, which is 2, is less than or equal to 5% of the population size, which is 300 million, then we assume independence, and this is the rule in the book. Okay, so once we get independence, we've got it now by this assumption here. Probability that both are left-handed. Okay, so we got independence. So let's take the probability that the first one is left-handed and the second one is left-handed. Remember, we're trying to get independence, so we've got that. So now we just multiply them together. Probability of L1 times probability of L2. Okay, and so this one is 0.13 times 0.13, and we get 0169. Okay. All right, now let's move on to the next question here. What's the probability at least one is right-handed? Okay. Now here we want to, again, list out every possible outcome, so the sample space. So let's take the first individual, the second individual, so left, right, left, right, left, right. Okay, and then we get the probabilities because all these are independent. So we just multiply 0.13 times the second one, 0.13 times 0.87, because if the probability is 13 left-handed, then 87 is right-handed. 0.87, 0.13, 0.87. So here we can get all these probabilities here. So we multiply 0.13 times 0.13, 0169. 0.13 times 0.87 is 1131, 1131, and 7569. 7569. And notice this is the sample space. If you add this up, you get 1. So now we just want to find all the ones that are at least 1 R. So that's going to be this one here. And we'll just highlight them. So at least one right-handed is here. At least one right-handed is here, and at least one right-handed is here. So the only one that's not at least one right-handed is that first one, and that first one there is both left-handed, right? Both left-handed. So we essentially want to add up this probability here. But if you'll notice, we can take 1, so we can use the complement rule here. So the probability of at least one right-handed is equal to 1 minus the probability that both are left, 0.169, and that gives us 9831, which is the same probability as if we add up this group of probability here. This is 0.9831, but the better option, the one you're going to have to use in the homework, is the complement. So the complement of at least 1 is none. Okay? So let's take one more example here. Okay, so this time we have a parallel structure of identical components. The system can succeed if at least one of the components succeeds. Assume the components fail independently. There we go. And that's in the homework in 5.3, you will always have independence. So that's really the main thing you want to focus on. They fail independently of each other, and each component has 0.15 probability of failure. So here's a system, parallel system. So notice electricity follows the path of least resistance. So in other words, it's going to go here and then it's going to follow. But if this one fails, then it's going to pick up and it's going to follow this track. But if this one fails, it's going to follow this track. So as long as one works, the system works, right? That's the idea. Okay? So what's the probability the one component fails? Well, that's 0.15, right? Probability, one component fail, 0.15. Probability two components fail. Well, since they're independent, then that's just 0.15 times 0.15. And we get 0.225. All right. So now, let's move to the next part here. Probability that a parallel structure with two components succeeds. So here I've drawn out parallel with two components, right? And the system will succeed as long as one of them succeeds, right? So let's again list out every possible occurrence. So we've got first component, second component. So it can either work or fail, and work, fail, work, fail. So both work, right? They're 0.85 times 0.85, so we multiply those together. And then fail is 1.5, fail is 0.15, 0.85, and fail is 0.15. So again, we can get all these probabilities, just multiply them out. So we get 0.7225, 1275, 1275, and 0225. Okay, so at least one working. Let's highlight those. Well, it's going to work here because both work. It's going to work here because the first one works. It's going to work here because the second one works. It's not going to work here. So we want this probability here. That's the probability. But remember, the total is 1, right? 1.0. So to get the probability, at least one component works, right? Probability. At least one component works. I want to know the probability of this, right? Probability at least is going to be these three, or 1 minus, take out this probability, 0.0225, and we're left with this probability, which is all the green, which is what we want. So 9,775. Okay. All right. So lastly, how many components would be needed in the structure so the probability the system will succeed is greater than 0.999? Well, the easy way to do this is just to make a table. So you just make a table: 1, 2, 3, 4, 5, and we might need to go maybe one more, don't know. So number of components, and probability system works. Okay. Well, if we have one component, the probability it works is 1 minus the probability that that it fails. Let's see. Well, if we have one component, probability of failure is 15, so the probability is 8.5, right? If we have two components, and remember, we take the total probability and we take out the case where both fail. That's 0.15 squared. And the rest of the probability left is the probability where we have at least one working. Same here, 0.15 cubed, 1 minus 0.15 to the fourth, 1 minus 0.15 to the fifth, 1 minus 0.15 to the sixth. So these are the complement rules that we're using here. And if you check all these numbers, you'll find that it's this one right here that gives us the correct answer. And this is 9,992,4,24063. So this probability is the first one. So we would need to add 5 components. So 5 components. Okay. All right. All right, so let's move on to 5.4. Okay, we're going to talk about conditional probability and the general multiplication rule. So conditional probability, again, this is red given. This vertical bar is red given. And the event E is what I think about as new information. Okay, and then we have the probability that 2 events occur when they're not independent is here, and I'll show you some examples of that. Okay, so let's take a very simple example. Suppose I have a deck of cards. Sample space would be ace of spades, king of spades, jack of spades. all the way down. There's no 1, but there's a 2. This is supposed to be 2 of hearts. So there's 52 cards in a deck. So let's let the event E be a draw 4. Well, how many elements is in E, right? Number in E. This is number in E. Well, there's 4 of those, right? How many red cards do we have? Number of elements in set F. Well, there's 26 of those. And E and F, red 4. This is together. So the number in E and F, there's 2 of those, 2 red 4s. So this is the definition really that's preferred. So we just take the number in E and F, which is 2, divided by the number in E. Probability E and E given F. This is supposed to be F. Okay, so E and F is 2, and then F is 26, and that's the probability. Okay, so we're essentially just taking the sample space and reducing down to only the new information, which is a red card. Red card. Okay, and out of the red cards, how many of those are 4s? Well, 2 out of the total red cards of 26, and that's the probability. Okay. All right. So let's try another example. So according to the U.S. Census Bureau, 17.9% of households are in the Northeast. 5.4 households earn $100,000 per year or more, and this is the key here, and located in the Northeast. Okay, so we've got E, home is located in the Northeast, so the probability of E is 17.9%, or we'll write it as 179. Probability of F, we don't know that, but we do know E and F, right? And that's 5.4%, so the probability of E and F is 5.4. So now we want to focus on this word given. Okay, find the probability that a randomly selected U.S. household earns more than $100,000 per year. So this one here, F, probability of F, given, right? That's where we draw the bar. The household is located in the Northeast. Okay, that's E. Okay, so we're going to use the definition here. This is probability of E and F divided by, and this piece here always goes in the denominator, probability of E. So do we have this information? E and F, yeah, we have that. And we have E is this. Okay, and so that's the probability. Three oh one seven. Okay, so let's try another one here. And this just gives us speeding tickets in terms of gender and number of tickets. So number of tickets. Okay, so we got a total of 197. What's the probability randomly selected individual was issued no tickets? Given, that's the key word. So probability of no tickets, will that be 0? Given female. And so the easy way to do it is restrict yourself to the females. So out of these 115, how many were written 0? So 97 over 115. Okay. So what's the probability a randomly selected individual is female? So this time we're going to be reversed. Probability female given 0 tickets. So this time we're going to restrict ourselves to the 0 ticket holders. Right? So there's 168 of those. And then how many of those are female? 97 over 168. So that's what we want. 97 over 168. Okay. All right, one more. Okay. So next page. Oops. Oh, I think there's only a couple. Okay. So you get the idea here. So let's move on to the very last question. Okay. So let's say that we have a bag of tulips. 30 tulips are purchased. So let's write that down. So 30 total. And we have 12 red. We have 10 yellow. And we have 8 purple. Okay. What's the probability that 2 randomly selected tulip bulbs are both red? And the key here is the sampling is done without replacement. Okay, so if we take one out, we don't put it back in. So what's the probability that both are red? Probability, first one is red, and the second one is red. This is the general multiplication rule. It's going to be the probability you get a red on the first one times the probability you get a red on the second, given that you got a red on the first. So probability the first one is red is 12 out of 30 times the probability second one is red, given, well, that's 11 out of 29. Okay. All right, so let's try this one. Probability the first one is red, the second is yellow. So probability we get a first one is red and the second one is yellow. So we'll just let these events here be this. So this is going to be probability the first one is red times probability the second one is yellow given the first one is red. So the first one is red is 12 out of 29. I'm sorry, 12 out of 30. And then we still have, now how many yellows do we have? We still have the same number of yellows. And we had, let's see, 10 yellows. So we got 10 out of 29. Okay. And then the next part, what's the probability the first one is yellow and the second one is red? So probability the first bulb is yellow, second one is red. Well, this will be the probability you get a yellow times the probability you get a red, given the first one was yellow. Okay, so again, 10 out of 30 times, we still have 12 out of 29, so you get the exact same thing here. Okay, and let's go ahead and give some. So here I got 132 over 870. Here I got 120 over 870 and 120 over 870. Okay, and then the last one. What's the probability that one is red and the other is yellow? So again, this is where you want to draw the tree diagram on this one. So the first one and the second one. So you can have a red, a yellow, or a purple. Here, red, yellow, or purple. Red, yellow, or purple. Red, yellow, or purple. Red, yellow, purple. Red, yellow, purple. Red, yellow, purple. So what's the probability you get one red and one yellow? Well, let's circle those. One red and one yellow. And we'll circle them. I'll just circle them in green. One red and one yellow can be here, and one red and one yellow can be here. So there's two ways that can happen, and we've got both of those probabilities from above. Okay, and so we just add them together here. So that's going to be the probability you get a red and a yellow, red on the first, yellow on the second, plus the probability you get a yellow on the first, which is this case here, and a red on the second. And so these are 120 over 870 plus 120 over 870, or 240 over 870. Okay, so this 5354, I hope this helps with the homework, and if you have any questions, please let me know, and we'll see you next time.